For example, on a distribution feeder, you might have maybe 100 distribution transformers, and from each distribution transformer you might have many tens of loads. So and each consumption load might be a household or a commercial establishment, and each household you might have tens or many tens of loads. So if you are looking at the actual load connection to the physical distribution system, it's a very large number. So even if a load has a failure of once in 5 years, if you have many thousands of loads, these faults are occurring all the time, and you need to be able to deal with that, especially when it is spread out around in a large geographical manner. And so your transmission and distribution system traditionally is more exposed to the problems, but on the flip side, you can make use of higher performance materials and components on a larger scale. You can have more sophisticated control and protection packages in the centralized system, where it may be justified based on economies of scale, whereas in DG systems it is typically co-located with the load, which means that it is less exposed to external disturbances. And so you can tune your reliability to match your load requirement rather than make it all very high or all very low. You can actually try to match the reliability requirement of the source with the load. And often DG is also people use it as a backup system when you don't have power from the grid. So overall, if you look at from the efficiency perspective and from the reliability perspective, what I believe is important is not that one method of addressing generation will solve all problems. It is a way in which you need to design your system such that both centralized and distributed generation they have to coexist. So it is not that the centralized system would go away and you would have only distributed sources, or you would never have distributed sources and everything is solved in a centralized manner. You need to have engineering architecture where both systems can actually coexist. So if you look at so we looked at it from a efficiency and reliability perspective. If you look at the typical upfront cost perspective, scale actually favors centralized power plant, where you have larger ratings of the centralized power plants, whereas the smaller ratings of the DG unit. So you have benefits of efficiency, economies of scale up to some extent. Once you go to very gigantic sizes, then again you have problems. But when you are talking about typical DG and centralized systems, you are talking about benefits of efficiencies of scale for the centralized systems. If you look at renewable DG systems like rooftop solar or combined heat and power systems, they are of a lower rating, typically maybe for a household or commercial rating. So you cannot use the level of sophistication or the advanced materials. You may not be able to use hydrogen cooling, for example, to cool the conductors of a residential synchronous machine, whereas you could actually easily use that. It's typically used in a large centralized generator. So whether it is again, as we mentioned, the DG doesn't have to be always renewable. It needn't always be a centralized power. Solar rooftop solar. It might be a small diesel generator that you have in your commercial establishment, which you use as a generation source, either as a backup or it might be used for some additional functionality, depending on the type of interconnection or power conditioning device. So again, if you look at the economics of scale issue, for each distributed generation system, you need to actually duplicate control and protection, and so you have some impact over there. But it is becoming less important nowadays, as you have sophisticated digital controllers which can handle not just the control of the DG unit, but also many aspects of the protection can be integrated into a single processor. So, you can actually have quite sophisticated protection and control methodologies even at lower power scales with the newer digital controllers. If you look at efficiency from the component efficiency point of view, from the machine efficiency point of view, you have advantages for the centralized power method of generation, whereas the overall efficiency, especially if you are making use of waste heat, you have advantage for the distributed type of solution. Again, when you look at the reliability from the use of high performance materials or cooling, you have advantages to the centralized power plant, but reliability is not just having high uptime, but if you look at reliability in terms of redundancy, you have, for example, if one large generator in a coal plant or goes down, you lose a large amount of generation, whereas if one turbine out of 250 turbines come down in a wind farm, you might lose 2 megawatts out of 250 megawatts. So, the redundancy actually gives you benefit in some of these methods. So, if you look at the societal needs for distributed generation, there are many issues which makes energy a pressing topic. It is an issue from the source side where you have concerns of resource depletion, you have concerns from the sink side after you make use of the energy. How do you deal with things like carbon dioxide, which is essentially addressing climate change issues. You also have issues of power quality. Is there energy at all in the first place? I mean, there's a very big societal cost of poor power quality, or lack of electricity being available is actually a big cost. Overall, for this course we don't have a standard textbook. We will be looking at papers from journals, we might make use of data sheets or technical reports from companies. You can make use of your power electronics or your power systems textbook that you use in your undergrad or in your courses that you would have done in your first and second semester. The first couple of books, one by Professor David McKay and the second by Emery Levens, they are actually more general reading. You don't need to have much technical background to actually read these things. Maybe you can ask your parents or relatives to also read it. They might be able to comfortably read those books. Okay. So this is similar in line to the small is profitable, similar to small is beautiful paradigm that E.F. Schumacher used to had a book, Small is Beautiful. So this is the overall introduction for the course. In the next class we will look at specific distributed generation technologies and how power electronics has an important role in those technologies. Thank you.
Okay, good morning. It's 9:30. Let's go ahead and start. My name is Mehdi Ferdowsi. I am the instructor of this course, EE353 Power Electronics. First of all, I would like to welcome you all to this class. If you are a new student, welcome to Rolla, Missouri. And also, if you are a returning student, welcome back. I hope you guys have had a very good summer. So there are a couple of things that I have to go through before actually we get started with the lecture. One of them is the Blackboard. I guess you all know how to use Blackboard, or you're going to learn pretty quick. If you look at the 353 section of Blackboard, there is a like an on-campus lecture section, and also there is a distance section. I'm trying to make sure these two are exactly identical. So if you click on one of them, this is the stuff that I actually uploaded yesterday afternoon. If you click on content, pretty much everything is there. I'm just trying to make everything simple and put everything under one folder so you don't have to look around and figure out what folder you're looking for. So we have the syllabus of the course, the schedule of the course, and I'm going to go through each one. Come in. And